Nice to see you all. Finally, Maria, that's here. So, finally. Now, this is the upstream security presentation. Try to cover as many things as possible. As we knew, various things that was done, was man, long time ago. The other ones are various projects you may or may not know about. And usually I present with one of these two characters, Saint on the left and Mike on the right, that unfortunately could not make it, so I'll have to do it all myself today. So, you already know everything about Ceph, so I'm going to skip the intro slides. It's the bee's knees and all that. Rook is less well known, so we're going to go over that a little bit. Rook is essentially the operator for storage in OpenShift or Kubernetes, and it deploys Ceph as a storage overlay on top of your compute plane. And it is interesting because it tries to automate even more management than what Ceph does, using the fact that it's running on a containerized fabric, so you can provision things dynamically, tries to do things around automating upgrades, although Ceph ADM is largely caught up with what Rook pioneered. In terms of history of Ceph, the reason why I have this slide is primarily that I'd like to point out this slide is an internal IBM thing to explain to management of Ceph. But the corner is our internal estimate of how much Ceph is out there, which we try to update twice a year. We estimate there are 6.5 exabytes out there based on the community survey, on the customers we have at IBM, the customers we have at Red Hat, the community usage that we know about as product managers. Counting on fingers, I can get to 4.2 exabytes. And projecting what we know versus what we don't know, we believe that 6.5 exabytes is a conservative estimate. The non-conservative estimate approaches 10. So this is definitely the most popular software-defined storage platform in, at least in open source, since proprietary vendors don't necessarily publish the numbers. Now, security practices harden a specific point of the infrastructure. Cherry-picking practices without a model of the threat and the attacker is not a good way to go. The joke usually goes that if you want to protect from all possible threats, you cast your computer in concrete, turn it off, throw it at the bottom of the ocean, and maybe then it's secure. But it's not a very useful computer, right? So you need to define what are you going to do to secure the system in the context of what threat model you're facing. Are you facing script kiddies, or the GRU, or the dreaded privileged insider? These are very different scenarios. Some of them want to steal your data, others are happy to just crypto lock you and hold you for ransom. Others may be satisfied just causing a disruption, or deleting files, or causing a transient denial of service. You need to define what threats are you protecting against, which ones are your priority, and pick your battles. Because it may be fun to say that you have to secure everything, and that's a very managerial thing to say. But if nothing is a priority, if everything is a priority, then nothing is. Something has to have the resourcing, and that has to be the part that is valuable for your threat model. So let's start from the network, since this is a distributed system after all. The public security zone is an entirely untrusted area of the cloud. These are the segments of the Ceph network in Ceph configuration. Public security zone is entirely untrusted. It could be in the internet as a whole, or just a network external to your cluster that you have no control over. Data transmissions crossing this zone should make use of encryption. Note that the public zone, as I just defined it, does not include the storage cluster front end, which in Ceph is called public_network. These are two different things. Which define this public network defines the storage front end and properly belongs in what is called the storage access zone. The Ceph client zone refers to networks accessing Ceph clients, like the object gateway at the server level, or the Ceph file system or block storage at really the true client level. Ceph clients are not always excluded from the public security zone. For instance, it's possible to expose the object gateways S3 or Swift interfaces in the public security zone. Next, the storage access zone is instead an internal network providing Ceph clients with access to the storage cluster itself. Finally, the cluster zone refers to the most internal network, providing storage nodes with connectivity for replication, heartbeat, backfill, and recovery tasks. This zone includes the Ceph cluster's backend network, called the cluster network in Ceph. Operators often run clear text traffic in the cluster zone, relying on the physical separation or VLAN separation of the network from all other traffic. This would not be a valid choice if your threat model includes privileged insiders. These four zones are separately mapped or combined depending on the use case and the threat model you have in use. Components spanning the boundary of two security zones with different cluster authentication requirements must be carefully configured, because those are the natural points for an intruder to attack to escalate privilege. They've reached a lower priority network, they want to escalate to a higher one, they go through the gateways that bridge the two. So these points need to be secured with the requirements of the highest of the two security zones that are being spanned. And in many cases, the security controls are the most obvious thing to check, since misconfiguration there is the most easily exploitable thing. And since you have, in case of an attack, certainty that that is a place that's going to be probed, you want to make doubly sure that those things are configured correct. Operators should consider exceeding zone requirements at integration points, which for a storage product is actually easier to accomplish than for a general purpose operating system. So let's not complain. For example, the cluster security zone can be isolated from other zones easily because there is no reason for it to connect to other zones. Conversely, an object gateway in the client security zone will need to access just about everything. The cluster's security zone's monitors, all the OSDs, will expose its API to the public security zone on 80 and 443. So we have all varieties in terms of access required by our daemons, but we do not need to apply the most permissive policy to everything. We can tailor things and be smart about it. Now, there is a section here that is about being the security team for an open source product, which is usually what Sage covers, since that's what they work on. These are primarily concerns about what happens when you move from community to IBM or community to Red Hat. What are the different challenges, or in the case of the slides they prepared, where are the challenges moving from Red Hat to IBM, which are very different security organizations, and they're very different companies, and they're very different security policies in terms of corporate interests. The product security team that Sage heads performs all the security activities across the life cycle of each release, essentially fixing CVEs and prioritizing works in those areas. Amusingly for me, because I'm a manager, I find it interesting that IBM and Red Hat, because one is a fully owned subsidiary of the other, have diametrically opposite policies, but for good reason. So if you look at security policies from IBM, the policy from IBM is fix everything with different timelines. If something is low priority or low severity, more properly, we have longer to fix it. And that makes sense, because if you think about it, the IBM customer doesn't want to think about this. They just want it to work. They don't want to see alarms coming from the security scanner, from an audit, or anything like that. Conversely, on the Red Hat front, there is an attempt which is led by Vincent Dana, VP of Security, which is to make the case that security efforts should be prioritized on the things that are really hard or that are really dangerous. Don't spend, there are 20,000 CVEs, give or take, every given year against Linux. But maybe less than 1,000 are really exploited or exploitable. Vincent makes a very convincing case that that's where the investment should go. And when you look at it from the Red Hat customer point of view, that makes sense because Red Hat is the trusted advisor for those customers that are integrating their own solution. So it's funny, but the thing works both ways. And since we have a product that ships in both companies, we have to satisfy both, which makes Sage's job interesting. The efforts throughout the first year at IBM have been in catching up with pre-existing CVEs that were low priority. As I just described, that was a requirement. And working on precedent Biden's attestation work. And generally automating things because there is no way to keep up with all the work that needs to be done that doesn't go through automation. As I was saying before, because it's IBM policy to fix everything, we are working to fix everything, but we're staggering the things that are high severity versus the ones that are low severity, and generally using common sense. The part where these things get annoying is that if you're using a container scanner, that will flag anything that's in the binaries, even if those binaries are somehow not reachable in the container. The canonical example would be, say, you have a container image that is a fat image, and there is a printing service in there. You just use the general purpose operating system. Storage layer can never get an intruder access to the print service as an exploit vector, so it's not exploitable. But in terms of policy, we have to fix that too. So starting with 6.1 last year, we started stripping the images, and the IBM images contain only the smallest possible subset of Linux that we can ship to avoid these red flags, because this becomes a customer problem. They use things like twist-lock to scan images, and the customer, again, doesn't want to think about what is that with twist-lock flag. They just don't want to see the flag, right? And there is enough of that already with the false positives. Sage is generally positive about the experience of transitioning to IBM, and that was a point that they tried to make here. There is also interesting work that's happening in terms of quantum crypto, because IBM has an internal mandate to secure everything against quantum exploits of traditional cryptography. We have different mandates for different technologies. Storage is one of the early ones. So we're looking at what is necessary to do that there for some. I was in the wrong slide when I was saying that. Okay. Now let's go back to the technical side instead of the organizational side. Moving on to encryption. Server-side operators overwhelmingly choose to encrypt data at rest using the Linux Unified Key Setup mechanism, more commonly known as LUKS. This has been the case for, I think, 8 years. It was below 50% when I joined, and then it quickly went over 50. And now it's so high, so above 90, that I don't even track the metric anymore. All data and metadata of the Ceph storage cluster can be secured using a variety of VM configurations, and almost all of Red Hat and IBM's customers choose to. It's universally present, and the performance, in fact, is negligible, so it's not even a consideration at this point, it's a default. We also enable security best practice by locating daemons, by locating monitors on separate hosts from their storage daemons, ensuring anti-affinity of the keys that encrypt the data and of the data itself. So because the keys for the OSD are kept in the monitor, and the monitor is somewhere else from where the OSD is, if somebody does physical attack against your data center and steals a machine, they have the data or they have the key, but they don't have both. They have to steal 2 machines and they have to steal the right 2 machines. But again, it depends on your threat profile. Is physical breach of your data center concerned or not? This, however, is easily done just by not co-locating monitors with OSDs, which used to be a best practice for a long time. It's not that common anymore now that with containers we can co-locate things, but if you're on the paranoid side of the spectrum and this fits your threat profile, absolutely go with this. The object store gateway has additional capabilities, including encryption at ingestion time, the use of per user keys as opposed to per drive keys, which tend to be the default. And RGW supports key rotation with tools like Vault, supports Amazon AWS SSC, KMS, and a few things more. Department of Defense ciphers, approved ciphers, like TIPS 142 and 143 soon, can be also used as supplied by RHEL in appropriate versions. For encryption in transit, network communication can be secured by turning on Ceph protocol encryption. This requires the messenger version 2.1 protocol, which was introduced with Nautilus. Here, clear text is common and generally fine in cases where privileged insiders are not concerned, because you can physically separate that network. However, the gains are rather limited because Ceph is a network distributed system. The latency introduced by encrypting the network is typically masked by the network latency itself. In some cases, you may need a little bit more CPU to make this work, but it's trivial, and we were just discussing with Dan that we probably should set this as a default. But it's not, and it's not super common right now because it's not the default. So yeah, logical or physical isolation, VLANs or separate networks prevail here for now. What else? Looking at more specific protocols, S3 service is usually secured between RGW and the S3 client with TLS. Although plain HTTP AP is obviously an option if you want it. Not very common anymore, but maybe you're serving images and you want to save that overhead. Now, TLS termination of these connections is at HA proxy. So securing the link between HA proxy and RGW is something that you want to look at, depending on what your network layout is. May or may not matter. Also, of course, with any network, standard network practices like firewalling individual nodes to only expose a clear list of ports really apply. They have applied for the last 20 years, but since people don't seem to uniformly do that, that's a reminder. Now, specific to Rook. Rook can use CRDs, custom resource definitions, to encode many of these settings, like configuring trust certificates for RGW's web server. Rook supports at-rest data encryption, as we discussed earlier, with in-flight Ceph protocol encryption supported starting with Rook 1.9. Kubernetes user permissions. The Kubernetes user permission system applies to persistent volumes, so permissions, quotas, and all that comes with that we get for free from Kubernetes, and Rook needs to do very little here. Rook also supports key management systems in the CSI, Container Storage Interface, with the driver allowing individual volumes to be encrypted with their own key, or limiting the scope for each key. This all ensures that we can follow best practices easily and automate them. This includes key rotation, revocation, limiting scope for each key, limiting the scope of unencrypted traffic, and so on. Now let's look at the control plane instead. As popularized by Ansible, SSH is used by Ceph ADM, Ansible, and other deployments, and they want tools to provide a secure command path for install and upgrade operations as part of host management. We do this pretty transparent. I think that the user experience with Ceph ADM has been stellar so far. We are at the point where upgrading the storage cluster is easier than upgrading the underlying operating system. So send a note to those run guys. There is also the fact that because we can do a rolling upgrade across nodes and take one node offline at a time, we have the ability to do all of these operations while the cluster is serving data and without having any user visible interruption or impact. Now, management dashboard is secured with TLS and 443, but where it can be accessed is usually something that's tailored by operators. They don't usually make the dashboard for a storage cluster available on the internet. Which of the network zones they want to expose that on depends on how much they are users of UI or not. There is a very strong community of Ceph users, especially in OpenStack, which are CLI aficionados, so or addicts, and so the result is dashboard may or may not be present depending on who the user is and who the operator is. We have options for SAML authorization and Kubernetes native authorization. And then those are the supports for the manager, which you also want to decide where they're exposed and where they should be reached, other than the Ceph clustering. Talking more about identity and access. So, Ceph's use of shared secret keys protects clusters from man-in-the-middle attacks by default. But good practices are still needed. A good practice here is to grant keyring, read, and write permissions only for the current user and root, with client admin user restricted to root only. This prevents all users from being root as per best practices. Talking now about RGW. RGW obviously supports the key and secret model of AWS S3 and equivalent model for OpenStack Swift. Of course, the administrator's key and secrets should be treated with the appropriate respect, and administrative users should be used sparingly to reduce the risk of accidental exposure. RGW's user data is stored in Ceph pools, which should be secured, as we discussed previously regarding data at rest. We can couple with OIDC providers, such as Keycloak, backed by your organizational identity provider, for even better granular role or distributed access, or attribute access. With identity and access, we support LDAP, Active Directory users. We often get customer questions about what does it take to use LDAP users as opposed to local users. And the answer is that there is no difference. And obviously for OpenStack, we support Keystone to authenticate users, not just in OpenStack, but also for object gateway users if you're using the object store for your applications, not just your cloud. Of course, in addition to identity management, auditing is also an important part of security. Operator actions against the cluster are logged and should be periodically reviewed and removed from the entire history. But you should have it for a few months to review incidents if any occur. And all of this should be aggregated to your log management system, whether it's RSyslog or Splunk or what have you, as obviously logging best practices. Now this one gets a little bit fun. Once data is deleted from a Ceph cluster, it cannot be generally recovered for practical use. There are exceptions, however. RBD has a newish, maybe not something anymore, called the trash bin, where you can make dynamic use of spare pool capacity to retain images that have been deleted until a certain time has elapsed or until that space needs to be reclaimed. So the data that you deleted is still there and in a recoverable state. Similarly, in RGW, it's S3, so versioning of object store buckets is to be expected. And that may result in deleted objects being preserved until they are purged by policy or by the administrator. So whenever user data retention is a concern, not just for security reasons, but for legal reasons, where you have to ensure that something has been truly deleted, configure your data storage pools accordingly. Additionally, like in any storage system, individual data blocks that used to constitute an object, file, or volume are still present on the physical media. And you cannot easily overwrite Ceph by writing a lot of data to it, like you would for a local hard drive. That's not going to work, or at least it's not going to work reliably, which is what you care about. Secure deletion or sanitization of media is another common question. And really the easiest way and most practical way to do this is to do the right thing to begin with, encrypt the drives. And when you sanitize the drives, you forget to keep. You have immediate sanitization of the data. And you also have other benefits, which include the fact that if you are not a very big buyer of hardware, you probably cannot return shredded drives. So you cannot have fun and take out your drive with a shotgun or put it in a shredder or even a degosser because the vendor wants to see a semi-functional drive to verify that it failed in the proper way to honor your warranty. So again, encryption wins one more time. And then there is the opposite scenario. The one where you want to make it harder to delete things. In other words, when you're being attacked by someone who wants to encrypt your data and do the ransomware thing. RGW is a facility for multi-factor authentication that is usually used in this context to prevent attacks where it's too easy to go and overwrite data with encrypted versions by adding a multi-factor authentication step in front of it. Now these are for the A+ students. Hardening options are highly vendor dependent and they are a big headache. These are Red Hat's choices, but they're, if you're using another operating system or another Ceph vendor, you may have other selections. We of course ship with SE Linux in enforcing mode. It's sort of a religion at Red Hat, but it makes sense, especially for a product of this kind where it's very hard for SE Linux to have any interference with user operations. We can make use of FIPS 140 ciphers as supplied by RHEL, and we are about to announce 140-3. That's coming next. The standard is being revised a little bit. And these are the options that we use to harden the binaries, not just the kernel. The kernel on one side, the binaries on the other. If you're building your own environment, you can generally expect that things like seccomp and pi will make sense. We also, I believe, have all of the ASLR options. Again, if you're using a different operating system or a different distribution, you want to check these out. Now, hopefully this was a little bit useful. You want to think about these things in advance, not after the incident. And we have a couple of notes for you, some bookmarks, things that are handy. Ronnie Osnat at Aquia Security has published a very nice tutorial on Kubernetes secrets. The key bit about Kubernetes secrets is that they aren't unless you configure them to be so. So that is mandatory read if you're doing this on Kubernetes. Michael Hausenblas and his co-author have also a very nice chapter on Kubernetes storage security in their O'Reilly book. The IBM and Red Hat products have also a data security and hardening guide, which is an entire manual, which is essentially the book version of this presentation. The Kubernetes documentation has interesting references about encrypting data at rest for the same reasons that I mentioned, referring to Ronnie's blog. And the last two are for those that really want to enjoy some pain with GCC flags and self-built kernels. The first one is blogged by Florian Weimer at Red Hat, and it goes over all the compile time options to harden binaries and what they do. So if you are into building your own binaries, you can study that. The second one is from Ubuntu team's security wiki, and that is a list of kernel hardening options. And it doesn't matter if you're using Ubuntu or some other OS. It's a very nice summary in terms of what the options are, and you can go and check your kernel configuration to see what belongs in your personal build if you're going to do that. And that's that.